Okay, for this part, we're finally going to get to one of the most obvious ways to test whether gene expression makes a difference. A cohort versus cohort comparison of gene expression, differential expression. So we're going to look at two different tests that people frequently use to test whether a difference exists. That's student's t-test and the Mann-Whitney u-test. We'll talk about each of these in succession. We're going to talk a little bit about the null hypothesis and its relationship to p-values. These are terms that frequently cause people some distress, so we'll try to walk through them carefully. And finally, we're going to talk about volcano plots. They're a way to visualize fold change and significance values that come from these difference tests. We've seen this slide before. Just a moment ago, we were talking about biclustering and about the use of machine learning for class prediction for biomarkers. Now in this case, we're going to talk about class comparison. We know the cohorts from which our patients come, and now we want to evaluate whether their gene expression values change between these two cohorts. In this case, we're going to be looking at the data for a particular gene separately from our examination of all the other genes. So in this case, I've highlighted 1294_AT. Just this particular gene probe is going to be used, and we're going to examine these three values for the HNE0 cohort versus the three values we see for the HNE60 cohort. In this case, I've called one set of columns the cases and the other set of columns the controls, but they're just labels at this point. Each different row is going to be a different test for difference. So in essence, we're going to ask, are the values from the cases from the same distribution as the values from the controls? Now, how do these tests work? I want to highlight that we often think of if the means of the two cohorts are very far apart, that we'll get a very clearly significant difference between the two. But there's also this question of how the data are spread around those means. So if you look at the two plots in this diagram, we see that on the left we have two Gaussian distributions, two normal distributions of data, in which the means are 1 and -1. And these data have a pretty good V between them. It's not what we call a baseline separation, but it is some separation that we can work with. At the right, we have a much shallower V forming between the two distributions. And the reason here is not a difference in the means. The reason for this to look so different is that the standard deviation of these data are different. So we still have a mean value of +1 and -1, but now the data are spread more widely. So when someone asks you, what does standard deviation mean? The simplest answer is skinny or thick. So in this case, on the left, we have skinny distributions with a low standard deviation, and on the right, we have a thick distribution where the standard deviations are twice the size. So both of these, the difference between the means and the width of the distribution around the mean, play a role in our ability to find a difference between cohorts. The way that these two difference tests find this difference between dispersion and difference between means is quite different. So student's t-test was created by a statistician named Gossett, who worked for the Guinness distillery, actually. So what he decided was that he would look for a difference between means. Now, it might not be apparent in that equation where the means come from, but you can see x sub 1 has a bar over it minus x sub 2 with a bar over it. Those are, in fact, the means of the x1 group and the mean of the x2 group. Then we divide that by the pooled standard deviation for both distributions, multiplied by the square root of 2 divided by the number of samples. So both the difference between the means and the spread of the data figure into our ability to find a difference. Now the Mann-Whitney u-test is quite different. We call this one a non-parametric test, meaning that it doesn't expect the data it's dealing with are necessarily bell curve shaped. They're not necessarily normal or Gaussian. Instead, it spends a lot of time focusing on the ranks of values. So if you might imagine I have 3 values of this cohort and 3 values of this cohort, it might be that all 3 of these are above all 3 of those. This is a case where we have a perfect separation between the two. You might have one value that's intermingled between the two. So we have a value from this hand and this hand, followed by one from this hand, followed by the final one from this one. So these different shuffles of orders, the ranks at which one cohort commingles with the other, give us the ability to discern whether the distributions are different or not. Okay, so in each case, these are going to produce what's called a test statistic. Student's t-test is called the t-test because it produces the value of t. Gossett found a way for us to evaluate what p-value, what probability, corresponds to that t-value. Similarly, the Mann-Whitney u-test produces a u-metric, and the u-metric can be converted to a p-value. So how do we evaluate what a p-value means? There's been a lot of back and forth about this in the literature. I hope that this will be both accurate and informative. So we want to determine the probability of a more extreme test statistic. So when we look at the t statistic that comes out of a comparison of this hump and this hump, we want to evaluate how likely it would be that a more extreme value would be seen. So you might imagine that if you scoot this distribution away in this direction or this distribution away in this direction, the t-value will climb in response to that. But how likely is that to happen under random circumstances, where these truly are one distribution? The null hypothesis assumes that the two cohorts have the same distribution. They have the same mean. They have the same standard deviation as well under the original student's t-test. Under this assumption, we must ask how probable is it that a higher or lower test statistic would happen by random chance alone. So Gossett's work back in 1908 described what the distribution of the t-statistic should look like, so we can compute those probabilities very accurately, and we call those p-values. So key concepts here. If you're doing a difference test, you really must know whether you're doing a paired or unpaired t-test. So the most common example that we find in paired t-tests is an example where we have the same people corresponding on both sides on both distributions. So imagine that you're evaluating weight loss. Does someone on this diet lose weight? You might have a weight before someone started the diet and a weight after someone started the diet, and you have this for 5 or 6 different people. Now, that means that you've got 5 before values and 5 after values, and now you want to ask, are the before values distributed the same as the after values? That is clearly a paired test. So if you do not tell the t-test that you're trying to do a paired t-test, you're not going to get the correct p-value out. You must inform it that before values and after values are linked in this way. This is patient 1, this is patient 1 over here. Now, one-sided and two-sided is something that more frequently people leave out, and they really shouldn't. If you are only looking for the genes that rise in expression in this difference, then really you only need to do a one-sided t-test. A one-sided t-test expects that the differences are all going to be in one direction, not the other. So if you were asking, do people's weights change by taking on a diet? That would be a two-sided test. But if you're saying, do people lose weight on this diet? That's clearly a one-sided proposition. And the p-values that you get from a one-sided t-test are twice as small as the values you get from a two-sided t-test. So it really does matter in whether you're going to find a difference or not. So how would you decide upon a difference test? Student's t-test assumes a normal distribution. I think many people know that, but it's a little hard for them to evaluate whether the data are normal or not. Frequently you have only 3 replicates, and there's really very little you can do with 3 replicates to tell whether they're normal or not. The Mann-Whitney u-test depends upon ranks, but if you have only 3 data points, you're not going to get very low p-values from a Mann-Whitney u-test. On the other hand, u-test is very good at resisting outliers. if you look at the data set in the upper right-hand corner, you can see that those two lists of numbers are exactly the same, except for the very last blue position. You see the last blue number atop reads 13.61, and the number below it is 25.61. So that's the only change we've made. Look at how much difference that makes in the t-test p-value. Pretty shocking, isn't it? Here we see that we had a p-value of 0.06 for the upper gene, but having changed just one value, the p-value got a lot worse. There's no chance that this is remotely close to significant. This change comes about because t-test cares how broadly the data are distributed. And when we add that very high outlier, 25.61, we see that t-test says, oh, hold on, I can't call this a significant difference by any stretch. Now, the u-test is much more stable under these circumstances. It gives the same p-value in both cases. And the reason is that the relative ranks do not change in these two collections. In both cases, the last blue value was rank number 1. It was the highest value in both cases. So making that number higher didn't change its rank to 0. There's no such thing. So u-test is much more robust against this. If you have a whole lot of replicates, 5, 6, 7, 20, then u-test and t-test are more or less interchangeable in how efficient they are with dealing with your data. And you might as well just use the u-test in those circumstances because it's robust against a lot of things that will cause t-test to crumple. But if you have too few data points, you really have no option there. Now, one of the things that limits us in t-test and u-test is that we don't have enough replicates to estimate variance correctly. So one of the things that we see in one of the major libraries available for analyzing these experiments, Limma, which is the Linear Models for Microarray Data. It's part of Bioconductor, which is a big library of bioinformatics bioinformatics routines that are available for the R statistical environment, is that it will allow you to do a t-test in a context where the variance does not come from just this one row of the table, just this one gene. Instead, it can use the data for all of the table to figure out what the variance really looks like in this range. As a result, Limma is actually a much better, more reliable t-test to use, so that the software doesn't think just for under random circumstances you happen to have low variance, that this gene has super low variance. It's going to use a broader variance, knowing what the other data look like. So Limma it has an awful lot of power for people who want to study this class of data set. I want to explain the Volcano plot, because the Volcano plot shows up a lot of the time. Now, I want to note that we're looking at two different dimensions for each gene. One is the p-value, but we don't plot just p-values here. Instead, we plot the negative log of the p-value. What that means is that we have a reversal. Instead of very low p-values being separated from very high p-values, we invert it. That in essence, the lower the p-value is, the higher it appears on a Volcano plot, and the higher the p-value, the lower it appears on the Volcano plot. The other dimension that we're considering for each gene is the fold change. So you might imagine that the signal is 3 times as great in cohort B as it is in cohort A. And for something like that, we would have a 3-to-1 fold change. You might imagine a different relationship where A was 3 times as big as B. In a case like that, we would say we had a 3-to-1 fold change. So we can think of one of these as a 1/3 versus 3 fold change. 1 to 3 versus 3-to-1. Now, that would be kind of confusing because now no change means we're at 1-to-1, and big changes towards B move away from 1 very rapidly, whereas changes in the other direction move close to 0, so they don't have as far to move. So one of the ways we address this is to look at log fold change instead. So on the log scale, a 1-to-1 ratio falls right at 0. And if you're doing log base 2, a 4-to-1 log change shows up at 2. A 2-to-1 ratio shows up at 1. A 1-to-2 ratio shows up at -1, and a 1-to-4 ratio shows up at -4. So both axes of a volcano plot are logs. Something at the middle doesn't have a large fold change. Something that's low has a high p-value. So volcano plots can be thought of in 6 regions. We start by separating values that are very high on the plot, points that are very high on the plot, from points that are very low on the plot. The points that are very high have the very lowest p-values. They're the differences we found significant by some t-test statistic or some moderated t-test statistic. The values down low we don't care about as much because they didn't achieve statistical significance. Next, I want to draw 2 more lines on here. I'm going to draw a line down the left, right here at -1, because this is a log base 2 fold change. And I'm going to draw another line north and south right here at 1 on this axis. That's, again, a log base 2 fold change. Now, why did I do that? Values that are very close to the middle of the volcano plot did not have a very big fold change. And the lines we drew separate things that had more than a 2-fold change up or more than a 2-fold change down on the outsides. So, in effect, what we care about are the differences that are large enough for a biologist to care about them, and typically that means having more than a 2-fold change in either direction, so the outer parts, and we care about things that produce a significant p-value. So in effect, we care about things that are outside our vertical lines and above our horizontal line. Those are the points that are labeled here in green on this upper left part and on this upper right part. That's how to read a volcano plot. So we had a lot of messages that to take away from this. Difference tests are used everywhere. Lots and lots of experiments, not just gene expression, make use of difference tests, whether they're t-tests, u-tests, or more complex ones like ANOVA. Differences can be detected best when the means are far apart and when the variance is minimal. So we want our data skinny and separated well. That's what gives you a low p-value. Volcano plots are a useful way to display lots and lots of genes all at once to reveal overall patterns of fold change and p-value. Sometimes they can help you to realize that your data are not performing the way that they would be expected to, that they don't look like a typical volcano plot. That is very worth knowing. So I hope that this is a useful overview for you on how to make use of difference tests in this context.